Chapter 1 Complex Numbers, Part 1. Why do complex numbers exist? Sometimes equations produce a negative number inside a square root. For example, we have here square root minus 4, which has no real number answer. To handle this, we define a new number, I is equal to square root minus 1. So I is equal to square root minus 1. Moving on, now we have imaginary versus complex numbers. An imaginary number, bi, where b is real, we have examples such as 7i, where b is equal to 7, and minus 2i, where b is equal to minus 2. And on to the next part, complex number. Z is equal to a plus bi, where both a and b are real. And the real part in this case is equal to a. The imaginary part would be the bi part. So how do we simplify square roots of negative numbers? If given a negative inside the square root, we first pull out the minus 1. So square root minus k is equal to square root k multiplied by I. Why is that? So minus k is equal to k multiplied by minus 1. Therefore, square root minus k is equal to square root k multiplied by minus 1, which is equal to square root k multiplied by square root minus 1. And of course, square root minus 1 is equal to I. Therefore, we end up with square root minus k is equal to square root k multiplied by I. Now let's take an example. Here we have square root minus 44. First thing we need to do is factor out the minus 1. So square root minus 44 is equal to square root 44 multiplied by minus 1. So the first thing we need to do is split the square root. So square root 44 multiplied by minus 1 would therefore be equal to square root 44 multiplied by square root minus 1. Now we replace the square root minus 1 with an I, and therefore we are left with square root 44 multiplied by I. Now we simplify the square root 44. So we break the 44 into a square number and a multiple that will give us 44. So in this case, 44 is equal to 4, which is a square number, multiplied by 11. And therefore, we end up with square root 44 is equal to square root 4 multiplied by square root 11, which is equal to 2 square root 11. 2 obviously from the square root 4. Put it all back together, we have square root minus 44, which is equal to square root 44 multiplied by I, which is then equal to 2 square root 11 multiplied by I. So all of this in brackets is equal to 2 square root 11 multiplied by I, and therefore our final answer would therefore be given square root minus 44 is equal to 2 square root 11 multiplied by I. Now moving on to the next part, which is the adding and subtracting of complex numbers. So when we add real parts together and imaginary parts together, we have example here like a plus bi plus c plus di. What we do is first we split into the real part, which is a plus c, and therefore we leave the imaginary part as b plus d multiplied by I. And if we have a negative instead of a plus, in this case a subtraction, we make it a minus c, again the real part, and plus b minus d, which is the imaginary part, multiplied by I. An example would be 3 plus 4i plus 5 minus 6i is equal to 8 minus 2i. Now we want to multiply by using a real number. We distribute the real number. So what that means is if we have k, which is a real number, we want to multiply with a plus bi, we end up with k multiplied by a, which is our first distribution of k, and then plus k multiplied by bi, which is the second part. An example would be 2 times 6 plus 5i in brackets is equal to 12 plus 10i. Now what we want to do is multiply two complex numbers. So first of all, what we want to do is expand the brackets. Then replace the I squared with a minus 1. So what that would imply is if we have a plus bi, and then we multiply that with c plus di, so this is one complex number, this is another complex number, we are left with a multiplied by c plus a multiplied by di plus b multiplied by ci plus b multiplied by d multiplied by I squared. And since we know that I squared is equal to minus 1, the last term becomes minus bd. So this will become minus bd. And this will obviously turn into AC minus BD in brackets, this is the real part, plus AD plus BC multiplied by I. This is the imaginary part. An example here would be 3 plus 4i in brackets multiplied by minus 5 plus 6i is equal to minus 39 minus 2i. Now moving on to powers of I, the repeating pattern. Because I squared is equal to minus 1, powers of I repeat every 4, or power of 4. So if we have I to the power 1 is equal to I squared, or I to the power of 2 is equal to minus 1. And then I to the power 3 is equal to minus I. And I to the power 4 is equal to 1. This then repeats. I to the power 5 is equal to I to the power 6 is equal to minus 1, etc. So you can imagine, obviously, I to the power 7 would be minus I to the power 8 is equal to 1. And moving on to quadratics that give complex answers. When we use the quadratic formula, x equals minus b plus minus square root b squared minus 4ac divided by 2a, if we have the discriminant b squared minus 4ac, which is here, becomes a negative, we have to rewrite that square root using I. And we have an example here of this equation that turns into x equals minus 2 plus minus I. How do we get here? So first of all, we have obviously the quadratic formula. A is equal to 1, as we can see, because we have 1x squared. B is equal to 4 because we have 4x, and then c is equal to 5 because we just have 5. Plug in the values, we should end up with x equals minus 4 plus minus square root of minus 4 divided by 2. Therefore, we are left with x is equal to minus 4 plus minus 2i, right? So we've got square root 4 multiplied by square root minus 1. That becomes 2i divided by 2. So therefore, we're left with our answer, x is equal to minus 2 plus minus I. Now moving on to complex conjugate. So here we have z is equal to a plus bi. The conjugate of z equals a plus bi is z star is equal to a minus bi. The key results from conjugates is that when we have z plus z star, this is equal to 2a. This is a real answer. And then with z multiplied by z star, we have a squared plus b squared as our answer, which are real answers. So the first one gives us a real answer, the second part is a real answer. So the imaginary parts are multiplied out or subtracted out, which we're going to find out how this works. So for z plus z star, this is equal to 2a. How does this happen? Well, you have a plus bi plus a minus bi, bi minus bi, they cancel out. We're only left with a plus a, which is equal to 2a. So this solves for z plus z star. And then in similar vein, if we have z multiplied by z star, what we do is a plus bi multiplied by a minus bi, both of which are in brackets. This gives us a squared minus abi all multiplied plus abi all multiplied. These cancel out. Then minus b squared multiplied by I squared. And remember, with I squared, that is equal to minus 1. So essentially we're left with a squared plus b squared. This is giving us, once again, a real answer. So all the imaginary parts are taken out. Here is an example. If we have z is equal to 3 minus 8i, then z star is equal to 3 plus 8i. This is equal to 6. Because all we have to do is just do 2a, 2 times a. So a is equal to 3 in both cases, so 2 times a is 6. Here we have z multiplied by z star, which is equal to 3 squared plus 8 squared. So that's a squared, which is a is equal to 3, and b squared, because b is equal to 8, and that should give us 73. When we think about conjugates on the plane are a reflection in the real axis. So z is a reflection in the real axis and gives us z star. So z is equal to a plus bi. When reflected, becomes z star, which is equal to a minus bi.